Moving on to our next topic, we have process capability. This topic will be introduced to you and be explored by me, Jen, and my partner, Luna. So before we start, here are the concepts that we must get to know first before exploring everything else. So first we have process capability. This is the inherent potential of a process output relative to what the consumer allows. It answers the question, can we consistently hit the target our customer has set? Next is process variability. This is the natural random spread in our output, the inherent noise from our equipment. So this is something that is built in the process already, so it cannot be changed or it cannot be avoided. It's measured by the standard deviation. This measurement is crucial because it defines the predictable operating range of our process. So specification tolerances is the limit that the customer or the engineer has set. Think of it like a border. If you go beyond this border, then your process is not within acceptable range. Now we have capability analysis. Capability analysis is a formal study that brings these two factors together. The study is only valid if the process is already in control. So it has to be stable and only exhibiting random variation. The goal here is we compare the process predictable range of variation. So three standard deviations against the customer's acceptable limits, the specifications. If our process predictable spreads fits inside the customer's limits, the process is capable of meeting the demand. But if it goes wider than that or goes beyond that, then it is not capable. And we must redesign the system to improve quality. Let's say our process is stable, but the variability is just too wide. It keeps going beyond the customer specifications. Since we can't ignore it, we have four main actions to address this. First, we can redesign the process. Maybe we need to invest in a new technology to simply shrink that variability. Second, the first method is not feasible. We might need to find an alternative process altogether that's inherently tighter. Third, we could just keep the process but implement a 100% inspection. This eliminates bad output, but remember, it's often very slow and expensive. And finally, the least costly of every one of these is to examine the specifications. Can we maybe manipulate the requirements without actually losing the customer satisfaction? That is the question. It's usually the fastest fix if possible. Process Capability Index. This is the most commonly used index when measuring the capability of a process to fit within the customer's limits. Crucial note, it must be computed only after the process is within control or stable. This is because the Process Capability Index is designed to predict the percentage of future output that will meet the customer specification. You can only make a reliable prediction if the process is operating consistently over time. The process capability ratio compares the total spread allowed by specifications to total natural spread of the process. The widely accepted standard for a process to be deemed to be capable is to have a capability index of at least 133. Although an index of perfectly 1 might seem that the process is just capable, even a slight deviation in the process for any reason would cause the process not to be capable. Using an index of at least 1.33 allows some leeway because it is not unusual for some processes to wobble a little bit from time to time. Sigma 6 capability. This is used when assessing the spread of the whole process. Since it is twice as big as a 3 standard deviation, its limit is also doubled, giving more room for processes to breathe and be accepted. The CPK index addresses the limitation of the basic CP index by considering the process means location relative to the specification limits. It is calculated as the minimum of the capability ratio for upper and lower limits, where each ratio is the difference between the limit and the process mean divided by 3 times the process standard deviation. The basic CP index can be misleading because it only compares the process spread, the 6 sigma deviation, to the specification range, ignoring the process means location. If the mean is not centered, the process raises tolerance on one side and raises the nonconformance on the other. The CPK index corrects this by always considering the worst case scenario, the specification limit closest to the mean, meaning the CPK will always be less than the CP index when the process is poorly centered. Therefore, the CPK index provides a true measure of capability as it penalizes a lack of centering. This is the formula for determining the CPK value in all its glory. Here we are getting the values of the upper CPK and the lower CPK index. Remember that the limiting factor is always the least of the two ratios. Since the upper CPK index is the one with the lower value of the two ratio, with 1.44, this is the limiting factor. In conclusion, since the CPK value of 144 is significantly larger than the threshold of 1.33, it is truly capable. And since the mean is closer to the upper specification, this is the reason why the upper index of 1.44 is the limiting factor and determines the overall CPK. Now, passing the cue to my partner Luna,